team AP047 from University of Mordor, Sri Lanka, and I just greeted you at the beginning. But how many of you have realized that? Fortunately, I am able to speak, so let me rephrase it. Hi, how are you? Imagine that I am a mute. Then I won't be able to present my ideas to you without the help of a person who knows sign language to do the interpretation for you, or without the help of another device. From the world's population, reportedly, a considerable amount of people suffer from various speech disorders such as muteness, apraxia, and aphasia. Most of the time, these are caused due to brain damage, tumors, strokes, or any other illness that may severely damage the brain, vocal cords, mouth, tongue, etc. So for these people to communicate with another human being, the only way for them to do so is through sign language. But most of us do not understand sign language. Therefore, we can see that there is a huge necessity to have a source of translation. But when it comes to countries like ours, the number of sign language interpreters is very less. For an example, as of 2018, there have been only 8 sign language interpreters for Sri Lanka. With the advancement of technology, many devices have emerged to serve this community. But what we saw was most of them, they did not offer a real-time sign language translation experience. Therefore, we thought to use the power of the FPGA board to solve this problem. EMG and IMU signals will be captured using the MYO armband, and then those data will be forwarded to the DE10 Nano FPGA board via Bluetooth. And then the preprocessing of that data and inferencing of a pre-trained neural network model will be done within the FPGA board itself. And then the produced classification output will be translated to text and speech. Next, in this short video, we will walk through our design procedure.
As the first step, we made our own dataset. So we handpicked a couple of gestures from the American Sign Language, and then we recorded multiple instances of it. So we had a data collection procedure, and according to that, we recorded approximately 30 repetitions of each gesture. All these waveforms were low-pass filtered, and we got the analytic waveform of it using the Hilbert transform. Then we got the envelope. So then came the hard part. We had to manually annotate each of these gesture instances according to their labels. So we annotated their EMG, accelerometer, gyro, and orientation data.
Even though inferencing of a neural network model was done using OpenCL, feature engineering and building a model was done using Python 3 in JupyterLab. First, we decided to plot the correlation matrices of different EMG signals for 3 different gestures. And these are the correlation matrices for the no gesture, for the water gesture, and for the yes gesture. After observing these correlation matrices, what we saw was all of these correlation matrices gave us a clear point that using all 8 EMG signals to train a certain model would be unnecessary. Therefore, we decided to use only 5 EMG signals after analyzing these correlation matrices. Next, we decided to use 6 features to represent or capture the characteristics or information contained in the envelope of a signal. And those features are energy, slope sign change, maximum value, skewness, kurtosis, and autoregressive coefficients. But we did not use these features as it is on all of the signals. To decide on what signals and what features to use exactly in our final model, we used 3 support vector machine classifiers that used only EMG signals and only gyroscope signals and only accelerometer signals for training. And in the support vector machine that used only EMG signals, we, after experimenting on different combinations of features, we ended up using the energy, slope sign change, skewness, and kurtosis features for the EMG signals. And this was the PCA plot we obtained, and this support vector machine was able to get an accuracy of 86% using only EMG signals. Next, we did the same for the support vector machine that used gyroscope signals. And finally, we ended up using the energy, maximum value, and slope sign change features to represent the gyroscope signals. And this was the PCA plot for these features. And this support vector machine was able to obtain an accuracy level of 96% using only these features. When we did the same procedure for the support vector machine that used accelerometer signals, we could not find a good combination that would result in an accuracy level as much as those of the previous two support vector machines. So, and also this is the PCA plot for the features used in the accelerometer signals, and what we observed was it could not capture the classes that much well as of the previous two signals, and the maximum accuracy level that it was able to obtain in this support vector machine was 79%. So finally we decided to only use EMG signals and gyroscope signals for our final model, and this the combination of features we used was the energy, slope sign change, skewness kurtosis for the EMG signals, and energy, slope sign change, maximum value for the gyroscope signals. And this support vector machine was able to obtain an accuracy level of 96%. After that, we used the same features and built a neural network model. So this is our neural network model, and we trained it for around 85 epochs, and we were able to obtain an accuracy level of 99% for the training set, 95% for the validation set, and 93% for the test set. Also, after observing this plot, we decided that these features and this neural network model will be sufficient to classify our 5 sign language gestures. But as the number of gestures increases, we will definitely have to expand this neural network.
So considering the performance of our design, instead of using a sequential language, we considered using OpenCL to parallelize our task. So this is how we use Intel OpenCL SDK for FPGA to convert our kernels into an AOCX executable file. So, and also we used Verilog to implement a UART communication between the Bluetooth module and the FPGA.
Data preprocessing and neural network inferencing involves lots of computations. Specifically, these include matrix multiplications with large number of elements. So we used OpenCL kernels to parallelize these tasks. Specifically, our design used 3 kernels to do inferencing calculations in the neural network. In matrix multiplication, each of the elements in the resulting kernel are calculated by a dedicated work item, thus it increases the performance. ReLU and softmax activations of the neurons are also done using kernels to increase performance. Even in an Intel UHD Graphics 620 GPU, the average time taken to classify a certain gesture was around 52 milliseconds.
Now I will be performing the thank you gesture in American Sign Language.
Thank you.
Next, I will be performing the yellow gesture in American Sign Language.
Yellow.
Next, the water gesture.
Water.
Next, again, the thank you gesture.
Thank you.
Next, the no gesture.
No.
So thank you for joining with us on our video. Please do share if you have any suggestions, comments, improvements which we can make. It will be really valuable for us. Thank you very much.